Hello students, in this video we are going to discuss the design of a beam under shear. In the previous classes, we have discussed the design of a beam under flexion, which means if you are given with a beam, then you are supposed to calculate the number of bars which are required to resist the flexion, which we have stated that AST. And if the bending moment is still more, then you will also design a steel at compression, which we have designated as ASC. And together we have termed it as area of steel. Area of steel, that is area of steel in compression, area of steel in tension. So from center of the tensile steel to the top fiber is called as effective depth small d, and this is called as width b. Now in shear, now we never discussed about the shear design. Shear is designed as a stirrup which is provided in this way. So you happen to see these are also called as rings, right? And this is rotated and this is tied to one of the bar. And if you happen to zoom it, this is the main bar, right? I have zoomed here. If this is the main bar, and your steel will come, your stirrup, and it will be rotated 135 degrees. Around the bar, and the same 135 degrees is rotated in back side of it, and it will come out something like that. So this is alternatively done, which means a steel rod, one that is bent something like this, then it is brought, then 90 degree bend, 90 degree bend, 90 degree bend, and 135 degrees, and it is tied. This is how it is made to the main steel bar. This is the main steel bar. Now we are going to discuss about the steel, right? This is called as if I cut any cross section, right? Now how many steel? Shear reinforcement I am cutting here is 2 times. So it is called as 2-legged stirrup. It is called as 2-legged stirrup. And if I have, for example, 3 bars here, 3 bars here, and it happens to be a heavy beam, then normally designers will also provide something like this. So if I cut here, then I am cutting 1, 2, 3, 4. This is 4-legged stirrup. This is 2-legged stirrup. This is 4-legged stirrup. It all depends upon the design. Now today we are going to discuss a design problem, right? Please note down this problem. An RCC beam 300 by 450 mm is reinforced with 3 numbers of 20 mm dia with an effective cover of 50 mm in tension zone. The ultimate shear at this section is 210 mm. Design the shear force. Use M20 and Fe415 grade steel. Sketch the reinforcement details. This happens to be a university problem which is given in November-December 2018 R16 regulation. So we will start the problem. Now given data, breadth as given as 300 mm, steel AST is given as 3 bars of 20 mm diameter. So this happens to come as 942.48 mm square. Then the other data which is given to you is ultimate shear force, which we denote by VU, is given as 210 kilonewton. He said it is the ultimate shear force. And M20 grade concrete, which means FCK is 20 MPa, and he has given 415, so Fy is 415 MPa. So for this data you need to design the shear reinforcement. How much is the dia and how much should be the spacing? That is what you need to do. So this is the cross section of the beam, and if I took the longitudinal section, if I take a longitudinal section something like this, then you will have main reinforcement running, right? And here will be the main reinforcement running, and your rings will come something like this. Right, so this will be tied something like this, and so this is how it looks. You need to design the diameter and the spacing. So the procedure is you are given with the certain data, and what is you are given with overall depth. So you need to calculate the effective depth. Effective depth small d is given by, see, when you have a cross section, when you have main reinforcement, to this main reinforcement now you have a ring which is coming, fine. Now what is small d is, so from center to the top of the fiber is called as effective depth small d. So in order to do that, you need to evaluate this and you need to deduct from D, capital D. So capital D minus D dash is what we need to calculate. This is D dash. So D is given by 450 minus D dash is given by half of diameter, half of his diameter is 20 by 2 plus you need to assume this diameter. Let us take this diameter as 10 diameter, take 10, and plus cover normally it is 25, but sometimes in textbook this is given directly. For sometimes in the question this is directly given. In your question this value d dash is directly given as 50 mm. You can take this as 50 mm. I read out the question. He said 3 bars of 20 mm diameter with an effective cover of 50 mm. So he given that. So I am willfully writing so that you have the practice of it if it is not given. So if you calculate this, 450 minus 25 minus 20 by 2 minus, so I'll take 8 mm on it rather than 10. Take 8 mm. So if I take 8 mm, you can take 10 mm also. This will come to 407 mm. And you need to immediately calculate maximum. You need to calculate nominal shear strength. Nominal shear strength tau v, which is given by VU by VD. You already got VU as 210 into 10 power 3 divided by B is 300, D is 407, and this will come around 2.8 MPa, which is very important now. Now, how much your concrete can take? So design shear strength you need to calculate immediately. Design shear strength. Tau C will depend upon two. One is PT percentage, which is percentage of reinforcement provided, and the grade of concrete, it is given as M20. What is the percentage of steel you get in? area of steel provided divided by cross section area into 100. Now area of steel provided is 942.48 and area of cross section BD is 300 into 407 into 100. Now if you go to table number 19, right? As per table number 19, PT percentage and with M20 grade concrete values are given, and 0.75 percentage it is 0.56, and for 1 the value is 0.62, right? So our PT percentage comes around 0.77. So the value is in between. So you need to calculate for 0.77 percentage what is the tau C value, right? So you need to interpolate it. So tau C, these values are tau C. Tau C is definitely greater than 0.56 because it is coming in between. So 0.56 plus difference of these two. Divided by difference of these two multiplied by this minus this or this minus this, whatever, but you have to get a positive value. So 0.77 minus 0.75. Okay, and if you calculate this, you are supposed to get this value as 0.565 MPa. Now this is the design strength and this is the expected strength which is coming. So due to load it is 2.8, so definitely shear reinforcement required. So as tau V is greater than tau C, shear reinforcement is must. Now when shear reinforcement is must, you need to calculate how much shear force it can get. So design shear force taken by reinforcement. Now you have a total shear force which is coming. Now this shear force 210, it is taken by two materials, concrete and steel, right? Sorry, right now. So VU is totally taken by concrete and steel. Fine. Now, if you want to calculate VUS, so you have to deduct VU minus VUC. So if you want to calculate how much steel the reinforcement is taken, then total shear force minus VUC. So I have deducted the shear force taken by the concrete from the total shear force. So VU is VU. Now how much is the concrete? How much shear force can concrete take, right? So force is given by stress into area. So you know the design strength of concrete, shear strength of concrete multiplied by area. Area is dt, right? So VU is 120 into, it is 210, right? 210 into 10 power 3 minus 0.48 is tau C. How much it is? 0.565. 0.565 into 300 into 407. Now you will get a value in kilonewtons. If you multiply by 10.3, you will get a value in kilonewton. Now these are the few steps, and you must remember these steps. First is you need to calculate this nominal shear strength which is coming due to load. Then you should be able to calculate the design shear strength of concrete. Then you need to suppose to compare them. If this is more, then you have to design the reinforcement. If this is very less, this compared to shear reinforcement is not at all required. Nominal shear reinforcement is enough. So what is this design shear reinforcement? So when you get this VUS, right? So you can provide these stirrups to the given shear force, because this value is always less than 210 mm. This value is always less than 210 mm. Fine. So the rest value 210 mm is taken by the concrete and the rest value is taken by steel. So in order to take that, code has given us which is given by the spacing of stirrups is given. Spacing of vertical stirrups. Spacing of vertical stirrups SV is given by 0.87 Fy ASV into T divided by VUS as per the code. Now, what is this ASV? As I said, if you want to provide two-legged stirrups, then 2 into pi by 4 of dia square would be the ASV. If you have provide four-legged stirrups, then it will be 4 times pi by 4 of dia square. So, because we are providing only 3 bars here, we are providing 3 bars, and the top bars we doesn't know. So we shall go for assuming two-legged stirrup only. Two-legged stirrup of, I have assumed 8 mm here, if you remember so. 8 mm diameter stirrup. So ASB will become 2 times pi by 4 into 8 square. This will give a value of 100.53 mm square. So back substituting it, spacing you will get as 0.87 into 415 into 100.53 into effective depth is 407 divided by VUS. You have to back substitute here. The value you will get from here, you have to substitute. This value SV you have to compare with the maximum spacing. The maximum spacing you can provide is 0.75. Sorry, it is a minimum. So 0.75 times D is 407. So this is 305.25 mm and 300. So as per codal provisions, the value which you have calculated, this value and this value, the least should be taken out of these three. Okay. So when you have completed it, I think you will get a value of 100 mm. So let me say I am taking the least possible. I am taking. So you have to state here, provide two-legged stirrup of 8 mm dia, edge rate 100 mm center to center. And if you have written this statement, the design of shear reinforcement is completed.